this video, I'm going to show you how to create a point cloud from simulation data and then convert this point cloud into a field so that it can be used in field-driven design so that you can add gradients to lattice geometry. I've started by creating this model here, which is a brake caliper from the automotive setting. I've applied some loads, boundary conditions and supports, and that is sufficient to run an analysis on this brake pedal that does not yet include a lattice geometry. I run the analysis. I can visualize the results in terms of stress on the part using the View Now button. We can see the gradient here. I've already done this, but I can use the callout tool to create callouts to place data at specific points. This is reading the field that is the results of the simulation. At these discrete points, we capture the stress or displacement, and then we can use this in field-driven design later. There's an option to view the data from each of the callouts in a table at the bottom of the screen. And you can edit the columns that appear in this table. So I'm going to remove displacement and factor of safety, leaving von Mises stress, and then I'm going to add the x, y, z position of each of the points. It's also a good idea to remove the units, although this is not strictly necessary. I'll now copy this data from the table and then paste it into an Excel spreadsheet or any other spreadsheet software. There's some unnecessary information that I'm going to delete, and then I'm going to move this first column to the end so that my data is now in the format of x in the first column, y in the second, z in the third, and stress in the fourth. Because of the way we handle units in Altair and Spire at the moment, I'm going to convert these from millimeters to meters by dividing by 1,000 for each of the positional coordinates. You can see the data is in essence the same, it's just an order of magnitude smaller. I'll overwrite the original data, and then I'll add some headings to each of the columns so that we know which is which. This is also what's expected when importing back into Inspire for field-driven design, so I do recommend adding this header. Once we're finished, we'll save and get ready to re-import this. Make sure you save it as a CSV file. We'll now return to Inspire, and what I'm going to do is to suppress a combine operation that I did before to make this one continuous part, and that allows me to separately edit this plate in the middle. I'm going to add a surface lattice to that and manually change the cell size to be 6 millimeters in each direction. I'll accept that for now, and what I'll do now is roll back the timeline to before the lattice was created and go to the point cloud button and then import the CSV file that I created earlier. You'll see the values populate in the table. After a quick check, it's okay to accept these. We need to rescale the point cloud information so that we go from stress into something more useful for our lattice design. And in the workflow that follows, I'm going to convert stress into relative density, which is in the range 0 to 100%. 0 being completely empty and 100% being fully dense or solid. To do this, I need to select the driving object, and that will be the point cloud that I've just created. Thinking back to my data, I need to put these minimum and maximum values in for the input range. Now, it says distance, but please ignore this because it doesn't just handle distance, it handles any scalar value. And these were approximately in the range 22 to 93 megapascals of stress. We have a units mismatch, so I'm multiplying by 1,000 to get into the correct scale for the conversion. Once this is done, I specify that the output range will be in percentage, and I'll clamp the values so they don't go above or below 0 or 100%. And I'm going to put some preliminary values for the relative density, let's say 50 and 75%, and accept this. I'm now going to roll forwards in time to bring the lattice back into the scene, and I'll edit that. If I go to the field-driven icon next to density, I can select field 1, which is the field I just made from the point cloud. It didn't look quite how I wanted it to, so I'm going to exaggerate the gradient a lot more. So now I'll set the minimum density to 20 and the maximum density to 80%. Let's see if that looks better. Yes, it's more obvious now, but I think we can push that even further. So I'll reduce 20% to 10%, and I'll increase 80% to 90%. Now we can clearly see that in areas of low stress we have a much thinner or less dense lattice in this region, and in areas of high stress we have a much more fully embodied or dense lattice to bear the load or the stress that's experienced in that location. This is in essence how we use point clouds to create field-driven effects in lattices, and more specifically, how we can use simulation data to create point clouds for the same purpose.